All right, welcome back again, everybody. Today we're going to be doing section 15.8, which is all about triple integrals in spherical coordinates. So the last section we learned triple integrals in cylindrical coordinates. Now we're going to get a whole new coordinate system that'll help us integrate certain objects that are better described in this new coordinate system. Let me pull up the slides and we'll get started. All right, here we go. The good news is this section is also relatively short, so the lecture won't be too long. The downside is that it does require a decent amount of 3D visualization. So give yourself some time to digest these ideas and digest this coordinate system, and just make sure you're comfortable with how things are depicted in this coordinate system. So here's the overview. We'll talk about the spherical coordinate system to start. Then we'll talk about converting between the Cartesian and spherical coordinate systems. And then we'll do triple integrals in spherical coordinates. And this is actually the little subsection where we're going to completely rework the Riemann integral again in terms of this new coordinate system. So hopefully by now, I say it every time, but hopefully I really do sound like a broken record by the time I get to here. So bear with it. All right. So here's the spherical coordinate system. In this system, a point that is in three-dimensional space, we'll call it the point P right here, it's represented by an ordered triple rho, theta, and phi, where rho is the length of this radius right here that leads up to the point from the origin. Theta is the same angle as we had in cylindrical coordinates, or same angle as in like polar coordinates. And then phi is the angle between the positive z-axis and this ray right here. So phi is this angle, just like so. That's what it is. A couple of things to note. Note that we're going to say that the radius rho is always greater than or equal to 0, and phi is always going to be between 0 and pi. So phi, this angle here, could tip all the way down at its extreme. That would be the angle pi. So one thing to take note of is that this is basically just a new coordinate system, and every point in space can be depicted or described using this coordinate system. It's just a different coordinate system, that's all. So every single point in R3 can be described using these three coordinates as they're described right here in this description. Now, one of the nice things about a different coordinate system, as we saw in the past, and as we're going to see again right now, is that it can describe certain objects in a more elegant way than they might be described in a different coordinate system. So here's a great example. Think about a sphere. So a sphere of radius capital R has a Cartesian equation given like this. So that's the sphere centered at the origin with radius capital R. In cylindrical coordinates, you could rewrite it as little r squared plus z squared equals capital R squared. But in spherical coordinates, it's literally just rho equals r. And it makes sense if you remember what rho is encoding. Rho is just encoding the distance from a point. I should say the distance from the origin to a point. So the distance from the origin to a point, if it's some fixed number, then you're going to be describing a sphere of radius capital R. So it's really elegant, right? When you're working in spherical coordinates, you get this elegant depiction or description of a sphere. There are some other nice representations. So for example, this equation here, theta equals c, describes a vertical half plane, like you see right here. And then phi equals c is actually a half cone. Again, think about what variables are present in this description and think about what variables are free. So if I say something like phi equals c, that means the radius rho can be anything, and the angle theta can be anything. And that's exactly what you're seeing with this this cone right here, right? The only stipulation is that this angle has to be c, and that's true for every point on this cone. Yeah, I should mention here, this is for when c is between 0 and pi over 2, and this is when c is between pi over 2 and pi. So you can talk about like the upper cone versus the lower cone. All right, so how do we convert between the systems? So now that we kind of have a feeling for the components, I should say, the coordinates of a point, how do we convert between Cartesian and spherical coordinates? So here's how we do it. Just given the figure that you see right here, we can see that we can describe the z-coordinate as rho cosine phi. And this is just using right triangle trigonometry, right? So basically, how could you describe this length right here and it's going to be rho times cosine of phi. Notice that this angle is equal to phi. That's because, oh, I forget the actual statement. What is it? Opposite interior angle theorem or something like that. Oh, alternate interior angle theorem says that if this angle is phi, this angle is also going to be phi if these two lines are parallel. So if we want to know the z coordinate, which is the length of this line segment, or the displacement of this line segment, I should say, or given by this line segment, it's going to be the the hypotenuse of this right triangle times cosine of this angle. So you get that z is equal to rho cosine phi. That's the way we represent z in spherical coordinates. We can also see from the same picture that this leg of the triangle here is going to be given by rho sine of phi. And again, this is using right triangle trigonometry. Sine would be, opposite over hypotenuse, essentially, right? So once you simplify that for r, you get that this is equal to rho sine phi. So that's the setup. We've got z, now we just need to get x and y, which we're going to do right now. Remember that we know x is given by r cosine theta, just from polar coordinates or cylindrical coordinates, and y is given by r sine of theta. So since we just found a formula for r, we can substitute it into these equations right here where you see r, and that gives us these equations right here. So do I say it in the next one? No, I'll say it right here. So this box right here, these are the equations that let you convert between Cartesian and Cartesian and spherical coordinates. The thing I wanted to point out here is this. Let me highlight it so it's easy to see. Rho sine phi, this is just r. So this is the lowercase r. Let me put it in blue just to match things up a bit, r. This is the r that you're seeing right here in this picture. So a way to remember these formulas is it's still just r cosine theta and r sine theta, except now what is r? R is rho sine phi. So notice phi is different from theta. There's two different angles going on here, theta and phi. And then the other thing that ties all these together is the distance formula, which is given right here. So the distance formula gives you that rho has to be equal to rho squared is x squared plus y squared plus z squared. And this is just using the good old distance formula, or even the formula for a sphere of radius rho, right? Okay, so altogether, these are the isomorphism equations for converting between Cartesian and spherical coordinates. So you do need to memorize these. Make sure you commit these to memory. The way that I remember them, frankly, is that x and y are still r cosine theta and r sine theta, just as they have been for quite a while, right? The only difference now is that r is rho sine phi, and that's how I remember it. So r cosine theta, r sine theta, and then z is rho cosine phi. So there's a little bit of an alternation there, right? You see it? Rho sine phi, rho cosine phi. That's the way that I remember it, all right? Okay, let's practice a little bit. And these ones I want you to try on your own first before we do them together. But here is a point given in spherical coordinates. And what I want you to try is I want you to try to plot the point by hand. So, give yourself some axes and try to plot the point by hand. And then I want you to try to find its rectangular coordinates. So go from spherical to rectangular. Right, so first example, first problem of the day, go ahead and think about it. And then, like I always say something out loud. It doesn't even have to be to anybody. It can be to yourself. It can be to your dog, your cat, your computer. Just say something out loud to give your brain that feedback to let you know if what you're saying makes sense. Right, and now go ahead and try to work it out on your own. Try to plot the point and then find the Cartesian representation of this point. All right, now let's do it together. One thing you got to remember is the order of the coordinates. So that's one thing you do have to get used to. Remember, it's rho theta, phi, right? So those are the order of the coordinates. So when you see this 2 in the front, actually, let me do this. This 2 right here, that's rho. And then pi over 4, that's theta. And pi over 3, that's phi. And remember, what this radius and these two angles are doing is they're giving us the exact location of a point in space, right? And that point looks like this. There it is. So you've got the radius rho as 2. You've got this angle tipping up from the x-axis as pi over 4. And then you've got this angle here, phi, tipping down from the vertical z-axis. That's phi, it's pi over 3. So basically, if you were to go this way and go this way and go out that far, that will land you at that point. That's what it is. Actually, since I said it this way, one thing that I will say, just personally speaking, I actually prefer to think of the angles before I think of the radius. In fact, other countries will do this too. So some other countries have different conventions for certain mathematical ideas, right? But I actually find it more intuitive, personally speaking, to think of it as this angle, and then how far out to go. So that's the way that I make sense of spherical coordinates, personally speaking, kind of like reversing the order, thinking of it as theta, phi, and then rho, kind of like turn this way, angled that way, and then go out that far. But you can make sense of it however you would like, whichever is going to work best for your intuition. All right, now that we have an idea of where the point is, let's use the conversion formulas, the isomorphism equations, and write this in Cartesian coordinates. All right, luckily we already know rho, theta, and phi, so the conversion to Cartesian coordinates is very quick. We just sub in what we know. There's rho, there's phi, there's theta. Multiply things, simplify things, and you get this for x. Similarly for y, you get that. And then for z, you get 1. So the Cartesian coordinates of this point in space are root 6 over 2, root 6 over 2, comma 1. Right? Not too bad, huh? Okay, let's do the other direction. So let's do another example. And here what I want you to do, I want you to try this one on your own first. I'm giving you the point in Cartesian coordinates, or rectangular coordinates, same thing. And I want you to convert it into spherical coordinates. So at the end, you should have a point that is given in terms of spherical coordinates, rho, theta, and phi. All right, so just as before, think about it for a moment. And now say something out loud about maybe what you would start with, or maybe say the formulas out loud if you can remember them already. And now try to work it out on your own. See if you can calculate what the spherical coordinates are going to be. And we'll do it together in just a moment. All right, here we go. So what we have given to us is x, y, and z. So since we know x, y, and z, we can recover rho pretty quickly. I think that's what I do first, yeah. So we know x, y, and z, so rho is going to be the square root of x squared plus y squared plus z squared. Remember, we chose rho to be the non-negative root, so we don't have to worry about a plus or minus in this case. We're specifically choosing the positive root just to make things easy. So when we simplify that result, we get 4 for the radius rho. And now we need to find phi and theta, so that's the goal. Now, we know that z equals rho cosine phi. And just using, again, kind of like right triangle trigonometry, we can recover what phi is by taking the arc cosine. So if z is equal to rho cosine phi, then if you solve this for cosine phi, you're basically dividing by rho, right? And you get this. But we have a number for z. Z is -2, so we can sub that in. We just found rho, so we can sub that in, and then we simplify to get -1/2. Now what we have is cosine of phi equals -1/2, and so what we have to ask ourselves is, what is an angle whose cosine is -1/2, that angle being in the interval from 0 to pi? And that one is going to be 2 pi over 3. So imagine the unit circle. I like to say that. Imagine the unit circle, and then figure out which angle that's going to be. All right, next, what else do we know? Oh yeah, we also know that x is equal to 0. So if x is equal to 0, that means this is equal to 0, and that means that cosine of theta has to be equal to 0. And again, what is an angle whose cosine is equal to 0 in that interval from 0 to 2 pi? Wait, 0 to 2 pi? What is it? Hold on, brain fart for a minute here. So yeah, it'll be pi over 2. And then, why are we not using 3 pi over 2? Hold on a sec. Let me pause for just a moment. Yes, sorry. Just definitely a brain fart. We're choosing pi over 2 because that's the restricted interval for to even define arc cosine, right? So the conventional restriction on cosine is 0 to pi. So if we want to do the inverse cosine of 0, it's going to be the angle in the interval 0 to pi where that's true, and that's going to be pi over 2. So basically the same reason as before. All right. So that's how you convert between the systems. You have a few questions on the homework about it. We'll do some questions on the activity about it. Now let's talk about integrating in this system. So things are going to get a little bit technical, but hopefully will sound very, very familiar. The way we're going to do this is we're going to rework the mechanicals for the Riemann integral again, so we can integrate in this new coordinate system when we'd like. So here's the familiar setup. Suppose we're given a continuous function f defined on a bounded region E, and we're going to contain that region E in a ball B, and the ball is going to be given in spherical coordinates. So rho phi theta is a point in R3, and we're saying that rho is between A and B, theta is between alpha and beta, and phi is between C and D. And some other stipulations, we're going to say A is non-negative, positive. We're going to say that B minus A is less than or equal to 2 pi, so there are no full rotations, or I shouldn't say there's not more than a full rotation involved. And this has got to be less than or equal to pi as well, for the same reasons that we don't have full swings from the top all the way to the bottom and around some more. So just some basic restrictions. We're going to define a capital F by using an indicator function as we've done a bunch of times now. So the indicator function just says yes on the set and no off the set. And now here's where it gets kind of fun. So in a spherical coordinate system, there is an analogous rectangle, and the rectangle is what we call a spherical wedge. This is a picture of what one of these spherical wedges looks like. It's kind of like, oh man, I feel like this is a good depiction here. It just, imagine there were a whole bunch of these, and if you had a whole bunch of them all stacked together and all around, you would basically create a full sphere, right? So it's called a spherical wedge. And what we're going to do is we're going to partition our ball B into a bunch of small spherical sub-wedges. This is what it looks like. How do we do it? Well, same thing as before. We divide each of those individual subintervals for each one of the coordinates into L, M, and N subintervals of length delta rho sub I, delta theta sub j, and delta phi sub k, respectively. Same thing as before, except now it's spherical. um, what is this wedge like pictorially, or what is it even like more descriptively? It's the region that's bounded by concentric spheres of radius rho sub I minus 1 and rho sub I. It's also bounded by the half planes given by theta sub j minus 1 and theta sub j, and the half cones given by theta sub k minus 1 and theta sub k. So you can imagine like that, right? Hopefully that helps a little bit, but just imagine a bunch of spheres and then slicing the spheres almost like an orange and then slicing them at an angle as well, and that'll give you one of these spherical subwedges. As before, we're going to choose a sample point in each one of these subwedges, sample point x, y, z, but I, j, k stars. And in order to do it effectively, we need to convert it into spherical coordinates. So we're going to use our spherical coordinate representation, which is going to look like this big mess. But just take a slow breath. Maybe that was a little too fast. Don't let the notation overwhelm you. This is one of those things in math where if you see this really nasty, gnarly, gross looking representation of something, it can be very off-putting. But really all this is the same isomorphism formula as we saw earlier. It's rho sine phi cosine theta, rho sine phi sine theta, and then rho cosine phi, x, y, and z. So that's really all it is. But it's for each one of these individual particular subwedges. That's why I've got all this extra stuff. Okay. Now, if our function f is integrable, looking ahead a little bit, then we can just choose the subintervals to have uniform lengths. So instead of indexing them by the particular subinterval, we can just say all of the subintervals have lengths delta rho, delta theta, and delta phi, respectively. Just keep everything uniform. And then the volume of each one of these subwedges is going to be given by this right here. So this is just computing the volume of each one of those, right? Now, simplifying this a little bit and shuffling things around, we get that the volume of each one of these subwedges is going to be rho squared sine phi, and then all the deltas right out here. Now, just like before, we evaluate capital F at each one of these sample points, and because of that indicator function, it's going to basically leave only what is on the set E, the only place where little f is defined. And then we can form the approximating Riemann sum, which looks like this. Again, don't let it overwhelm you. Just look at the pieces and recognize the structure. It's really just evaluating f at x, y, and z. And then the volume of each one of those wedges, like the volume of each one of those rectangles, is given by this factor right here. That's what it is. Then we take the limit as the volume of those things goes to 0, or equivalently as the partition gets more refined, Lm and n go to infinity, and then we find the following Riemann integral, this. There it is. Okay. If the function f is continuous, then Fubini's theorem also allows us to integrate iteratively, and we have this representation below. This is the representation of a triple integral in spherical coordinates. So it's f evaluated at the point, and then this is now what that differential form is going to look like, that volume form. So just as a reminder from previous sections, remember we're going to scan between two surfaces, and then we're going to scan between two curves, and then we're going to scan between two numbers. That's the rough idea, right? So a couple of important points to note here. Just like in section 15.7, this is really just a change of variable in the integral. That's really all it is. We're changing the variables with which we want to integrate, and all of this stuff is really just being modified to reflect that change. So that's what's actually going on here. I also want you to note carefully this additional factor that appears, rho squared sine phi. So this factor is necessary when you do this change of variable, because this is letting you change the volume of that rectangle so that it's appropriately scaled to be in terms of a spherical rectangle. That's basically what it is. So one thing you might ask yourself is, man, we've seen this kind of thing happen before. Maybe is there a general structure to that factor that just depends on how we change the variable? Maybe. Have to think about it. All right. So now that we have the setup, now that we know we've got our coordinates and we know how to integrate, let's do an example. So here we go. I want you to, this one you can try on your own. It might be a little bit tricky, but you can try it on your own, and then we'll compare our results in just a minute. I want you to try to use spherical coordinates to find the volume of this region that you see here. Kind of looks like, very loosely like a hot air balloon, you know what I mean? So what is it? It's the region that lies above this cone and below this sphere. All right, so above that cone and below that sphere, they actually meet at this boundary right here. So this is one where I want you to think about it for a minute, right? Ponder it, look at it. Okay, now say something out loud about the problem or what you might try. Anything to give your brain that feedback, right? And now try to work it out, and we're going to do it again, or we're going to do it together in just a moment. All right, here we go. So first thing is, because we're going to use spherical coordinates, we need to be able to describe this region in terms of spherical coordinates. We have information about the region given here. We just have to convert this information to a spherical representation. So one thing that can help is if you complete the square over here, you can find the standard equation of the sphere, or maybe even just from the picture, you can see what the equation is going to be. So this is the standard equation of the sphere shown right here, right there. So the sphere would actually go all the way around, right? But we're only going to be taking the top half. So one reason this is helpful is this tells us that the center of the sphere is at the point 0, 0, 1/2, which you can see from the picture as well. Okay, now how do we get this in terms of spherical coordinates? We know the sphere. Now we need to figure out how to describe the top part of the sphere in terms of spherical coordinates. So remember that one of the isomorphism equations is this: rho squared equals x squared plus y squared plus z squared. And we also know that z is equal to rho cosine phi. So because our sphere is represented like so, we can just substitute in these values and then we'll be able to find out what rho is equal to. So here we go. Here's our sphere, right? But this is equal to rho squared, and this is equal to rho cosine phi. So there you go. Now that rho squared is equal to rho cosine phi, for non-zero radius, we can divide by rho, and then we get that rho is equal to cosine of phi. So now we know the extent of rho in this case, the radius. Now let's look at the cone. So the equation of the cone is given by this formula, and now we're literally going to plug in our equations for x, y, and z and see what we get. So here I am substituting in the equation for x, and then the equation for y, and then the equation for z, and then simplifying. So you go through a simplification, factor some things, use the Pythagorean identity right here to get 1, take a square root, and then what you get is that rho cosine phi is equal to rho sine phi. And this means that cosine phi has to be equal to sine phi. So this is going to yield that theta has to be pi over 4, just as we would expect from looking at this picture. It's kind of that halfway angle, right? Halfway angle. Okay. Now we can describe the region using polar coordinates. We've got all of the representations and we can see all of the bounds now. So theta is going to go from 0 to 2 pi. So remember, theta is this angle. It's like the horizontal circle. So theta is going to go from 0 to 2 pi. That's how we'll integrate in terms of theta. Phi is going to go from 0 to pi over 4. So phi is actually going to go from here to here, to pi over 4. That's where we're getting those bounds, okay? And then rho is going to go from 0 to cosine of phi. So rho is going to shoot out like so, okay? Now, let me show this next figure because I think this figure is just really, really good at explaining how we're doing this. Learning how to integrate in these different coordinate systems really it's like a learned skill. You have to practice it. The best advice I can give you is that you are still scanning a region and you need to describe how you would scan the region, and you have to visualize it in your head if you can. Just try to think about how you would actually cover the whole region if you had to scan in terms of a radius and then a phi angle and then a theta angle, or in some order, right? So I'm actually going to, well, I'll do it in the order depicted here, but this is showing how we would scan in terms of the radius rho. So it's going to go out that far. And then we're going to go out that far on each one of these little slices. And the slice is given by the angle phi. So the slice is given by the angle phi. And then what we're going to do is we're going to add up all of those slices as you go around the circle. Maybe like, wait, this way. There we go. This way. And that's what this is depicting here. So shoot out that far, tip down that much, and then swing around by whatever angle. And if you do that in those 3 dimensions, you will cover the entire region. So that's how we're going to scan it. All right. Now, because we're finding the volume here, and frankly, the unit function is continuous, so we can use Houdini's theorem, and we can iterate the integration process, and this is what the iterated integral will look like. Remember, the volume formula is just integrating the unit function, 1, and that's what's here. It's kind of like an invisible 1. And then here's that extra factor we need to recognize that we've converted to spherical coordinates. And then here we're integrating rho from 0 to cosine phi, phi from 0 to pi over 4, and then theta from 0 to 2 pi. Right. The only variable that's involved here, or variables, are rho and phi. So we can split this up into 2 integrals. We can split it up into an integral in terms of theta, and then an integral in terms of rho and phi. And we can integrate with respect to rho first. And when we do so, we get this. Okay. All right. Now we can evaluate this integral separately as well, and that's where we're getting this 2 pi. And then what we're left with is this right here, sine phi cosine cubed phi. This is a standard trigonometric integral in terms of phi. So you can use the techniques that you remember from Calc 2 to evaluate it. And what you'll get is this, pretty much just a u sub, or a substitution, right? And then apply FTC2 to it, simplify, and you get pi over 8. And that's the idea. Right, so on that note, let's play. That's the whole section. Hopefully some of it just sounded like the same thing I've been saying a whole bunch of times. I guess the last thing I'll say is just practice visualizing, scanning those regions. That's really what it is. You have to figure out how to scan those regions. It just takes practice, okay? But you can definitely do it. Ask questions in class, do the activities, talk to your group mates, and I'll stop rambling, let you all go, and I'll see you next time. Thank you for watching.